Hi, and welcome back to this introduction of trigonometry. This is the second lesson. In the first session, we learned that the sine and, of course, the cosine, but we talked about the sine because it was easier to dissect and dismantle those vertical segment length from the y-axis, pull them out, and they were representing the tip of this rotating vector. Remember the rotating vector that we used to break up the total force into vertical and horizontal. So we pulled them out and we created an animation for them, and we called it the sine function or the sinusoidal function. It was a wave function. So basically the sine function, we found out that y equals sine of x or sine of alpha or theta or any angle. It's basically a function of frequency that repeats the same cycle as time goes by. So it keeps repeating the same pattern, the same cycle, going from 0 to 1, back to 0, then minus 1, and then back to 1. Back to 0. So, and it repeats this in different intervals of times, okay? So, and those intervals of time, they could be large, they could be small, they could shrink and be like, instead of the 360 degrees, the 2 pi could be only pi or pi over 2, or they could be stretched, and they could be, instead of 360 degrees, they could be 720 degrees, or 3 rotations, or 4 rotations, and so on and so forth. And we also learned that, let's go switch back here to the tablet, we learned that a standard, an angle in standard position has its vertex on the origin, okay? That's in math, we call the standard position for a vector is when a vector has its vertex at the origin, and we have one of its ray is on the positive x-axis, and this will be the initial side, and the terminal side will be the vector itself. And the amount of rotation counterclockwise here is your degree. So 1 degree, we said, or 60 degrees, or 30 degrees, or 120 degrees, which is 1 out of the 360. This is called the amount of rotation, and it's the angle we're interested in, we're forming. Most of the time it's counterclockwise, sometimes it's clockwise. We will study that in Quadrant 4. And for us to calculate this standard angle in a Quadrant 1, it's very easy because its reference angle is the same. We said we use a reference angle to help us calculate the standard angle that we're interested in. Especially in Quadrant 2 or 3 or 4, or if we have a negative angle that we have started with a clockwise direction and we want to go back to an angle, starting angle between 0 and 360. And even if we have, let's say, an angle that is above 360, that has more rotation, that had rotated counterclockwise more, let's say an angle that is, I don't know, maybe 405 degrees, 405 degrees. So this one has passed the first rotation. So we said our goal is always to arrive at a starting angle between 0 and 360. This is where in the first unit circle. So all we need to do is to find something we said called coterminal angle, meaning we minus this 360 to start at the first angle in the first unit circle. Our goal is to arrive at that particular angle between 0 and 360, and we find that it's 45. So the angle would be 45. Okay, so each standard angle has a reference angle. In Quadrant 1, the standard angle is its own reference angle, because we said the definition of a reference angle is an acute angle between the terminal side of this angle and the x-axis. You know, this is best illustrated and conceptualized in actually quadrant 2. So if I have an angle of 120 degrees here, okay, that's my standard angle. This is my amount of rotation. I'm going 120 degrees counterclockwise. So how do I, relate to, how do I calculate the sine and the cosine, the breakup? How am I going to break up this vector, this total force? I need to take into consideration this other angle that, look, because I want to use the tip of the vector. Remember, we use the tip of the vector to draw this perpendicular. That's why from each tip of the vector, we draw a perpendicular. And for every drawn angle, whether it's in quadrant 1 or 2 or 3, there should be then a reference angle, the angle that is formed by the end, by the terminal side, the vector here, the terminal side, and the x-axis. So this is going to be my reference angle. In quadrant 1, the standard angle is the actual acute angle formed by the terminal side and the x-axis. It's its own reference angle. But in quadrant 2, when I draw from the tip of the vector, once you remember the tip of the vector, you don't need to memorize anything. Remember, we talked about this tip of the vector, and it's the ignition key, because from this tip of the vector, you should remember that it's rotating. You can break it up. The sine and cosine, you're studying the breakup of this vector in vertical, in a vertical position, and the horizontal component of this vector in relation compared to the total force, or to the total vector. So when the tip of the vector is in quadrant 2, and if I am to draw, or this perpendicular to the x-axis, I'm going to draw it on this side. So it's relating to this reference angle between the terminal this time and the actual x-axis. So it should be 60 degrees. So it's 180 minus 120. My reference angle in quadrant 2 for 120 degree angle standard position is 60 degrees. Now if I go to quadrant 3, it's the same concept. Let's say I go from here and I go 240 degrees. If you go 240 degrees, this is your standard angle. You're still within the goal. You're between 0 and 360. You're within that first unit circle, within the first rotation. Okay? You don't need to add or minus 360 to go back to the starting angle. So all you need to do is just find that reference angle. The reference angle is the acute angle between the terminal side and the actual x-axis, which is this one right here. So it's 240 minus 180, it's again 60 degrees. 240 minus your pi minus this, the 180 degrees, this is 60 degrees. Okay? Now, in quadrant 4, if you have an angle, let's say, that is here, and you go clockwise, minus 60. If you go clockwise minus 60, what do? You go 360 degrees, okay, minus your 60. So it's 360 degrees minus this 60, you get to 300 degrees. So this is your angle, because your angle now, it's on this side. This is your angle. From here to here. Your starting angle is 300, okay? So if you go into this, you're going negative, yes, minus 60. But when you do your completion of this first 360 degrees, all you need to do is just minus the 60. You're not doing minus 60. If you do minus 60, you're going to end up, above the first rotation. Remember, the goal is to arrive at a starting angle between 0 and 360. So even if you're going in the minus direction, in the counterclockwise, you're still gonna minus it. If the angle is, I don't know, 45 degrees here, you know, you're going minus 45, so you do 360 minus 45 and you arrive at 315. Okay, so again, tip of the vector, this is very important, and from that tip of the vector you drop a perpendicular from the terminal ray of a standard position angle to the x-axis, and this is how you build this reference triangle. So this reference angle builds a reference right triangle, of course. And then all you need to do is go ahead, if you're in quadrant 2, do 180 minus that standard angle. If you're in quadrant 3, you do the terminal side minus the 180. And if you are in quadrant 4, you take the whole rotation, 360, and you minus that whatever minus or whatever clockwise rotation you went through. If you went 60 degrees, you do 360 minus 60. If you went 45 degrees clockwise underneath the x-axis, you do 360 minus 45 to arrive at 315. The goal, remember the goal, the only thing we need to remember is that the goal is to arrive at a starting angle between, your starting angle should be between 0 and 360, okay? So, that being said, now let's actually do a few examples here. So if you have an angle that is greater than 360 or is negative, we can find the equivalent, the non-negative, the coterminal angle, this starting angle between 0 and 360 by, like I said, either adding 360 or minusing 360. So if you have an angle, we did that, 405, which is above the first rotation, you minus 360 and you go back to an angle between 0 and 360, which is 45. Now let's say you have an angle that is more than 1 or 2 rotation. Let's take an example, theta equal 800 degrees. Okay, so you come and you do, okay, let me go back and minus 360. What do I get? You get 440. Yeah, but you're still above the first rotation. You're not within the goal that you set for yourself between 0 and 360. So you're going to do another minus 360. So you do another minus 360 and you arrive at 80 degrees. So you did basically 2 rotation backwards in order to get to your 80 degrees. And your 80 degrees is even a very, very easy angle because it's in quadrant 1. It is its own reference angle. Okay. So now let's say you were given an angle in the negative, which is minus 30 degrees, which means we're here. And you came this way, clockwise, minus 30. So what do? You do minus 30 degrees, you add 360 degrees to get out of the darkness. That's what I call it. Now, you're not gonna minus that 360 degrees, okay? You're gonna add the 360 degrees to get out of the darkness. And if you add a full rotation from here, going 360, what do you arrive at? What's 360 minus 30? Simple math. It's 330 degrees. So your angle, your standard angle, the goal that you set for yourself is 330 and is in quadrant 4. And, you know, we can deal with it because it's within the first rotation. Okay? So all you need to think about in order not to confuse yourself, when you have a negative clockwise rotation, think about getting out of the darkness. So you're not minusing the 360. No, you are adding the 360 to get out of this darkness. Okay? Now, I promised in the first lesson that most of us know the degrees, you know, to touch on the subject of what is a radian. You know, how did mathematicians come up with this radian thing? And why do we even use it if we have the degrees? If we were able to split thousands of years ago this unit circle into 360 degrees, and we said 1 degree is 1 out of the 360, and it seems to be working very well. Now the radian basically, and we're gonna explain it in details, was created to help find the areas of the sectors. It's a measurement actually created to fit the arc length all the way around the circle, which is a little bit more than 6 times the radius, or more precisely 6.28, the length of the radius. So the whole circumference is 360, or 2 pi, and we're going to find out why. What's that pi? However, if we take a piece of the arc length of a circle whose length is the same as the length of the radius, then the central angle that subtends that arc is called 1 radian, or a radian, or 1 radian. Okay, I'm gonna go to the board, and we're gonna do it on the board so we can get a better understanding of what I'm talking about. Okay, let me just, I think I have something here for you. Actually, no, let's go to the board and let's erase that hexagon. We will get to the hexagon very soon, maybe after this. So, an area of a sector, what does that mean? So, okay, let's first, if we have a circle, okay, if you have any circle, and we have that vector here, okay, and you're breaking it up. If the vector is here, the tip of the vector, you drop the perpendicular, and then you're making a chord actually, you're making a right triangle, and you are making a chord between this tip of the vector and this point. And again here, between this tip of the vector and this point. So, but you're not making a connection, all the way around the actual arc length. There is an arc length here that is subtended. This is not your perpendicular drop from the tip of the vector. And this is not the actual chord formed between, the tip of the vector and another point on that circle. So, if this whole circle is made out of a rope or a rubber band or a string, what can we do? Can we do something about it? Can we pull it out? Yes, we can pull it out. And here, let's go back to the tablet. First, we're talking about a sector. So the area of the sector. Part of a circle, okay? Now when you take the tip of the vector and you drop it, you're making a perpendicular. And here you do have what? Between this point and this point, you have a chord, okay? So the chord is a straight line. The perpendicular is a straight line. But actually this angle, this amount of rotation, is related to the subtended arc, which is part of the circumference, okay? So in order for to create a measurement that fit this arc length around the circle, mathematician needed to come up with a better measurement, because it has to fit. Look, if we want to find out the area of this segment now, and we're going to get to that in details when we study the advanced circle. This is the segment, okay? The area of this segment is actually the area of the sector, the whole thing, minus the area of the triangle, okay? So, again, there is a subtended length here. This one, we call it S in math, that is part of the circumference, okay? This subtended length that is part of the circumference is actually related to the circumference, and we can study it in relation to the diameter also and the radius. And what do I mean by this? Okay, let's think about it as, let's do this. Hold on one second. And okay, so let's think about it as, like I said, a circle made out of a rope or made out of a string or a rubber band, okay? And this opening, okay, this angle, this amount of rotation is actually related to the circumference, this curve, and it's also related to what? To the diameter. Because remember, if you pull out that diameter out of the circle that is made out of a rope, if you do diameter times 3, you won't cover the, that's what the early mathematician, now we know it as a fact, but this is how they started, okay? If you take that diameter and you multiply it by 3, you won't cover the whole circumference. You need a tiny little bit more to cover the whole circumference, okay? So, and if you do this radius times 6, you also won't cover the whole circumference. So you won't be able to make a circle, basically. You need just a tiny bit more than 3 with the diameter to cover the whole circumference and make the circle perfect. And you need just a tiny little bit more than the 6 to make, times the radius, to make this curve perfect and, you know, and everything proportional in this curve. So basically this, after trials and trials and trials, they came up to the realization that this value, it's a value basically, that they need to multiply the diameter by in order to make the circle perfect, the curve perfect, and in order to make everything proportional. And I will explain in a second what does that mean, proportional. Everything is proportional with relation to conic section, because a circle is also a part of, is the main conic section. Okay, so this value, it's a value that it never ends. It's your 3.14, 15, 92, and it keeps going and going and going forever. And that's what they call the 1 radian, or your pi, okay? So if you're going from one end, if you pull out that diameter and you want to go from one end of that diameter chord to the other end, you need to do diameter times 3.14, 15, 92, the whole value that never ends, in order to complete a full circle, a full curve. If you're taking the radius, you need to do radius times 6.28 in order to, you know, fit the arc length that is part of that whole circumference and make everything perfect, okay? Because at the end, even if you have a very tiny angle here on 1 degree or 2 degrees, it's a curve, it's a subtended angle, it's not a straight line, okay? So in order for us to make and keep everything proportional, we should never forget about the 0.14, 15, 92. If we just take, you know, diameter times 3, it won't work. So this 0.14, 15, 92 is basically your little value that is going to make everything proportional. And when I say proportional, what do I mean by proportional? Now, if I am studying the subtended angle, which in math we call S, okay, and in the sine and cosine and a coordinate Cartesian grid, I said sine theta equal opposite divided by the total force, or the vertical breakup divided by the total force, right? Which is y divided by the total vector, or the hypotenuse in this situation, mathematically speaking. Now, if I am in a sector, okay, and I want to study the same proportionality, I go theta equal this subtended arc length, okay, the curve, divided by r. Now, when is S equal R? When is, if in a unit circle R equal 1, when does it happen that S equal R? It happens, S equal R happens when theta in radian is going to be 1. And that's your radian, and that's your pi. It happens at, in degrees, 57.32 degrees. At 57.32 degrees, this subtended curved arc length that is part of a curve that is going to make everything proportional equals R, okay? And theta, you have a new measurement, it's 1, but 1 what? This is the 1 radian, this is your pi, which they call the 3.141592, happens at 57.32 degrees. And this is where your pi is. So if your pi is here, then if you go, we go inside a circle, we can go like this now. This is my 90 degrees. Okay. And I have a little bit, you know, this is my first 1 radian, 1 radian, and this will be your 2 radian. I'm sorry, it's not that great. This will be your 3 radian. The 3 radian is not going to be here. That's the whole point. The 3 radian is not going to be here. You need 3.141592. You keep going till you really cover that half circle, till you go from one end of the diameter chord to the other end. In order for you to go from one end of the diameter chord to the other end, you need more than that 3 new measurement that they came up with. This 3 new measurement where S equal R, and that in that situation theta, the angle formed or the central angle of a sector, equal S divided by R equal 1. And this is your radian, okay? And this happens at 57.32 degrees. So it's not at 60. If it happened at 60, you do 60 times 3, and you can cover the half circle with 3 of that new measurements. It happens at 57.32 degrees. So that's why you need a little bit more than 3 to cover this half circle, and a little bit more than 6, which is 6.28, in order to cover the whole circle, okay? And this is where the idea of radian as a measurement came from. Now, what I meant by proportional, this whole thing needs to be in line and proportional to the conic section and to the general formula of a conic section. Remember, if you can go back to my lessons on conic sections and general formula, it's ax squared, there is no b, you can review why there is no b, plus cy squared plus dx plus ey plus f equals 0. This is the general formula of a conic section. The main conic section that gets squished and gives you the ellipse, or, you know, is your circle, basically. And we said, when we studied the conic section, if there are many conditions, A is not equal to C, and the product of A and C coefficient is larger than 0, you have an ellipse. If it's less than 0, you have a hyperbola. If it's either A equals 0 or C equals 0, but not both, of course, then you have a parabola. We talked about all that, but we said if A times C is greater than 0, but A equals C, then we have a circle. And we gave many examples. I believe one of them was this one, x squared minus 8x plus y squared plus, let me see, 10y equal minus 41. And we said, even though you have all these big numbers, coefficients with the d and the e, you have 10, 8, A equals C. So potentially we have a circle here, not an ellipse. But using 3.141592 as a factor for all proportionals and proportionalities and ratios created with the coefficients A equals C, this is what puts all the pieces of the puzzle together. This needs to be in line with C equal pi times d, not 3 times d, not 3 of that new measurement times the diameter. 3.1415, 92, and so on and so forth of this new measurement that really actually happens right where the angle in degrees equal 57.32 ... Okay, so this new opening or this new measurement happens at 57.32 degrees, almost. It's not really actually, it's almost 57.32 degrees, and it's very in line with the coefficients A equals C and everything being in in proportionality within the circle. Okay, so again, everything is always linked together and everything is always connected together. Now, since we are at it, we need to think about, in many books, when they teach you this, they teach you, oh, the area of a sector equals, and that's a formula that you need to remember. I don't remember it myself. So they teach you area of a sector equals half, or they write half, times length of the length of the arc times the radius. And you have to remember that. And actually, this area of a sector comes up a lot in many standardized testing, like SATs and ACTs. But again, I'm gonna go ahead and teach you something that you should do not only with this, but with any shapes, forms, and area of study that has a lot of proportionalities and all its ratios and proportions connect together. What do I mean by this? Let's say you have a cone inside a cone, a small cone inside a big cone. Can you say the volume of the small cone divided by the volume of the larger cone is proportional to the height of the small cone divided by the height of the large cone? Yes, you can. And we're going to do the same thing here. Equivalent fraction with part, very simple math, very simple arithmetic, divided by whole. We're going to start, training our brain to work this way. What do I mean by this? When you have volumes and areas, especially, and heights and altitudes, area of a sector, what we need to find out, divided by what? Area of the whole circle equals what? It's proportional to what? You can do whatever you want. To this S, which is part of what? Of the whole circumference. Circumference. It's also proportional to what? To the angles, remember, created by this S. Theta, and the whole thing is 360. Or theta and radian divided by 2 pi. Very simple. So now using, what I need, which one can I use here? I can use the area of a sector, that's what I need, divided by the area of the circle, pi r squared, equal what? I need S divided by the circumference, 2 pi r. And all I need to do is just, cross multiplication. So area, what I need to find out, times 2 pi r equal S times pi r squared. Eliminate, and you get rid of the square, get rid of this, and A equal what? 1 divided by 2 S times r. There's no pi in it. There you go, and there you have it. So basically, again, these are little tricks and little things that will help us memorize less, and that's it's always our goal. Now, I had a question yesterday, how do I find out the S, the length of an arc? It's like we said, we are using this S subtended length of the arc within the same concept that we use to find the sine, or we say the sine of an angle theta is the vertical breakup y divided by the total vector the terminal side or your total force, which in this case is the hypotenuse. And we said here, when you have a sector, whether it's a tiny sector or a larger sector, theta in radian breakup equals what? What's in front of it on the opposite side? The S divided by R. Okay? So if you want to find S equal theta times R. And again, I don't memorize it because I remember that in a sector, I use the same breakup that I use for a sine because the subtended arc length is on the opposite side of the angle. And I go theta instead of sine theta, theta equal S divided by R. So S equal theta times R. So let's say they gave me a theta that is equal, let's say 135 degrees. And they tell me, find the arc length. What do you do? Okay, and you come and you tell me we need to use it in radians. And that's what we're going to start learning, how to quickly switch and convert between radian and degrees. This is your 3 pi over 4, okay? Because 3 times 3 pi over 4. Pi, if you think about it as completing the circle, though, so that's 3 times basically 180 divided by 4. Okay, that's one way of figuring this out, but we're going to learn other ways also. So I have 3 pi divided by 4 as my theta. I need my R. They should give you the R, or, you know, it depends on the math word problem. If you figured out the R, or they give you the R, I believe let's do something easy. Let's say R is 10 centimeter. So S equal R times theta. And this, again, we got that from the same breakup that we use for the sine. Theta equal S divided opposite to the angle divided by R. Okay, so basically this is the area within a sector. Okay, so theta is, R is 10 and theta is 135 degrees, which is 3 pi divided by 4. One way, we're going to learn other ways of finding this out, is the pi. It's completes actually, it's always 180 degrees. So if it's a number that you can multiply by 18 or 180, if it's an easy number like here, 3 times 180 divided by 4 is 135. Okay, so basically we get 30 pi divided by 4, and 30 divided by 4 is what? Is 7.5. I still haven't used the calculator, if you notice. 7.5 pi. This is a 5, I'm sorry. Now, if you want to use, you can leave it like this. Depends if you have a choice of A, B, C, D, and you know, one of the choices is 7.5 pi. Or you can go ahead, you know, if they want you to get the actual answer, it will be, I believe, let me see here. Okay, 23.56 centimeter. 23.56 centimeter. And there you have it. So now, we understood what a radian is. This measurement that was created to help us figure out this arc length, because the distances are not between the tip of the vector and the other points are not always in. They can form this knit around the circle that will create the triangles, it's very close to the circumference, but it's not really the actual circumference. That's why we are studying S, the actual curve, the actual circumference, okay? And that's why they created this radian. And you need, in order to go from one end of the diameter to the other end, you need more than 3 of this new measurement, the radian. You need 3.141592 and so on and so forth. So that's why they discovered that this radian actually happens exactly around 57.32 degrees, okay? And this radian help us also find the areas of the sector, and the areas of the sector, if we minus the areas of the rectangles, the triangles from them, we find the areas of this tiny small, remember here, segment here. So area of this segment is going to be equaling the area of the whole sector minus the area of the triangle. And we will get to those. We'll do a lot of examples on these. They're very easy. Once we know how to convert radians and degrees and all that good stuff. And we also learned that the area of a sector equals 1 or half of S, the arc length, times radius. And I taught you, remember this one very well. You're going to need it. Whenever you have heights, altitudes, areas, volumes, things that are proportionals, shapes that are proportionals. We said area of a sector, we can use our fractions, divided by area of circle, equal the arc length, the length of this arc, divided by the whole circumference of the circles, equal or is proportional to theta in degrees divided by 360 degrees, equal the radian or the angle theta in radian divided by 2 pi. And we can choose whichever fraction or equivalent fraction we need here in order to calculate the fourth element. Okay? Now, with that being said, I'm gonna finish this video or this lesson number 2 on one note. In your books, you learn in grade 8 and 9 and 10 that the easiest way to remember what a sine and a cosine and a tangent is so ka to wa. Meaning sine is opposite divided by hypotenuse, and cosine is adjacent divided by hypotenuse, and tangent is opposite divided by adjacent. That's fine. You can remember it this way if you already know it. However, we have a lot of identities and, functions and cofunctions and double angle identities and half angle identities and sum and products and all that good stuff. So we need more than that. We need our hexagon. We are going to start with the hexagon in the next lesson, in lesson number 3. And the hexagon is actually a great way to memorize less and to minimize the number of formulas and identities that are thrown at you in trigonometry. Okay, so in trigonometry, the best way, in my humble opinion, is to use the they call it the magical or the magic hexagon. I just call it the TSC hexagon, and we're gonna get to that in the next lesson. But for now, like I said, just remember how to use your proportions. Very simple math of small areas divided by the larger areas, or small volume divided by the larger volume, small height divided by the larger height, and they're all equal, and you can come up with your formulas using these proportions. Okay, and I will see you in the next lesson, in the next video. Thank you.